Hello, everyone. Welcome to N27 real life stoichiometry examples. Our goal here today is to go through some examples, obviously, real life, of stoichiometry, have you try them out on your own, and then we'll go over them together to make sure we understand the process and talk about it. So the first one we're going to look at has to do with airbags. I think we're all familiar with airbags in cars and the safety precautions. So how airbags work, obviously we need an exact quantity of nitrogen gas must be produced in an instant to inflate the bag faster than you coming, head forward to the steering wheel or the windshield. So got to be prepared for that one. The reaction is shown as this. NaNA3 is a solid. It produces sodium and nitrogen gas. Again, instantaneously is our goal. So obviously we need to balance the reaction. Take a moment and do that. All right, we are back. Hopefully this is the reaction that you guys got with balancing, and we should have no problems there. So here's the goal. If an airbag is made with 90 grams of NaN3, will it be safe? Assume that 65.1 liters of nitrogen gas are needed to inflate the airbag to the proper size to protect you during an accident. A hint, make the NaN3 your A value. We've talked about A, B values in the process of doing stoichiometry. The density of nitrogen gas at this temperature is about 0.916 grams per liter. So I'm going to pause it now. I'd like you guys to do this one on your own. When you've finished, hold up or turn on or hit the raise hand in Zoom, and then we'll go from there. All right, ready, set, go. All right, we are back. So here's our setup. We want to go from grams of A, which was given. Got to convert that to moles of A using molar mass. And then to get to moles of B, we have to use the mole ratio in the balanced chemical equation. And then once I have moles of B, then I'll use the molar mass to get to grams. And then as the question said, I needed liters. So we were given the density, and we used that number. As you can see here at the bottom, grams of A cancels, moles of A cancels, moles of B cancels, and then grams cancels again, giving us liters of B, which is nitrogen gas, which is what we are trying to solve for. Any questions on the setup here? Okay. When you plug everything in, we're going to get 63.52 liters of gas. Again, reminder, we needed 65.1 liters of gas to be safe. So it's not safe. The airbag will not inflate all the way, which again could be dangerous in the process. Any questions on this problem? All righty then. Let's look at example number 2, rocket fuel. In 1967, the Saturn V rocket did an unmanned test flight to the moon. It used kerosene fuel to get through the atmosphere into the outer space. Into outer space, not V, yay. The kerosene, its formula C12H26, combusts with liquid oxygen on board the rocket to form carbon dioxide and water. See, it took off getting a little bit higher up there. So our reaction, as we can see here at the top, the combustion of kerosene. So if the Saturn V rocket was loaded with 770,886 liters of kerosene fuel and 890,650 liters of liquid oxygen, would it have enough liquid oxygen on board to use up all the kerosene in order to get out of the atmosphere? So our goal here is to determine, looking at both reactants, is there enough to completely consume the kerosene with the amount of liquid oxygen. So, quick little hint for you. Make kerosene your A value. We know the density of kerosene is 749 grams per liter, and the density of liquid oxygen is about 1,141 grams per liter. So, again, our goal, how much oxygen is required to react with a known amount of kerosene. And then we can compare that to how much oxygen that we have. I'll pause it here so you guys can do this problem, stoichiometry, and then we'll come back. Again, when you are done, raise the hand on Zoom so I know where everyone's at, and then we'll go from there. All right, ready, set, go. All right, we are back. Oh, lost my picture. All right, so here's our goal. We know that kerosene is our A value as given. We know that oxygen is our B value, the thing we're solving for. So this is not LA like Los Angeles. This is liters of A converted to grams of A using density. Then we'll take our grams of A to moles of A using molar mass, which you can figure out with the periodic table. Then, where'd my mouse go? There it is. We'll do moles of A to moles of B. So the mole ratio based on the coefficients of B to A, because remember, we're solving for B, it's got to be on top. Well, once we get moles of B, then I can get to grams of B using the molar mass of oxygen. And then, again, we're solving for liters, so I'll use the density to get to liters of B, not LB as in pounds, but liters of B. And then below, you can see that we took the volume of kerosene given, and then we did our conversion to grams, moles of kerosene, the mole ratio to get to moles of oxygen, the molar mass of oxygen, and the density of oxygen. Any questions on this setup? Okay. Well, the answer we get is 1,758,801 liters of liquid oxygen needed. Well, according to our lovely problem, we don't have enough liquid O2 on board to burn all the kerosene. That might be a problem trying to get this rocket into outer space. Remember, we had 890,000 and some change of liquid O2. Clearly, we don't have enough. Questions on this problem? Alrighty then. Alright, example number 3, hydrogen-powered bicycles. I think these things are actually going to happen, or maybe they already are, just not in mass production. But electric bicycles are becoming very popular these days. They typically have a rechargeable battery pack, an electric hub motor. I have seen electric bicycles, hydrogen-powered, I have not come across. The new electricity sources combined a hydrogen fuel cell with sodium silicide fuel cartridge. This actually was a winner of Green Chemistry Challenge Award. I don't remember what year, but it was a winner. So, hydrogen-powered bicycles. The sodium silicide reacts with water to make the hydrogen fuel to run the bicycle. So, our equation here in the blue of sodium silicide reacting with water to produce some sodium silicon oxide compound, and then there's their hydrogen gas. So we're going to start with 1 kilogram of sodium silicide. Your tank can hold 500 milliliters of water. Will you have enough water to use up the battery? Now again, our battery is the sodium silicide, so I have a known amount of sodium silicide, and I need to know how much water is needed to completely react with the 1 kilogram of sodium silicide. Now keep in mind, I have 500 milliliters. but I want to know how much I actually need to react to completely consume the sodium silicide. So again, your quick hint at the bottom, we're going to use 1 kilogram of sodium silicide as my A value. And then the density of water we know is 1 gram per milliliter. Known thing. All right, again, I will pause it here for you guys to work on this on your own. Please, again, hold up your raise hand sign in Zoom when you are done and you got your answer, and then we will go from there. All right, ready, set, and go. All right, we are back. Thank you again for working on this problem. Let's go over it together. So at the top, remember we said sodium silicide is my A value. I was solving for water because I want to know how much water is needed to completely react with the 1 kilogram of sodium silicide. So if I set up my molar highway, we're going to go kilogram of A to grams of A. That's just a metric conversion, easy enough. Well, once I have grams of A to moles of A, molar mass, nothing new there. Been doing that for a while now. And then I got to get from moles of A, which is sodium silicide, to moles of B, which is water, using the mole ratio, which is the key to stoichiometry. Well, once I have moles of B, to get back to grams of B, I use molar mass. Easy enough, periodic table. And then lastly, I want to convert my grams of oxygen to milliliters of oxygen using the density, sorry, not oxygen, I apologize, grams of water to milliliters of water using the density of water. As we can see at the bottom, our string of calculations, again, kilogram, everything cancels out except for milliliter, which is what we're solving for. And my answer is 881.95 milliliters of water are needed to use up 1 kilogram of sodium silicide in the battery. Now remember, we only had 500 milliliters of water in there. So obviously we don't have enough to actually use up the entire battery, which means I guess the battery could be used even longer. Any questions on this? Alrighty then. Thank you very much. That is it for this practice problem, and we'll see you on the flip side. Peace out.